If you're a physics student, you've probably heard the name Irodov. His problems are legendary for being tough, but you know what? They're pure gold for building real, solid intuition. So today, we're going to tackle a classic orbital mechanics problem right from his textbook. And our goal isn't just to get the right answer, it's to really feel the beautiful, interconnected physics that makes our solar system tick.
So it all starts with this one simple fact. A year on Jupiter is 12 of our years. Now, that's not just a fun piece of trivia. It's a clue. It's a single, powerful piece of information that, once we apply the right laws of physics, is going to unlock a whole cascade of secrets about Jupiter's entire orbit. Let's dive in and see how.
All right, first things first, we need to figure out the distance. Just how much farther away from the Sun is Jupiter than we are? This is all about the fundamental architecture of our solar system. Okay, so here's the exact wording from Irodov problem 1.201. We're told Jupiter's orbital period is 12 times Earth's, and to make our lives easier, we assume the orbits are perfect circles. The mission for part A is crystal clear. Find the ratio of Jupiter's distance from the Sun to Earth's distance.
The secret key to unlocking this first part is Kepler's third law. And it's not called the law of harmony for nothing. It reveals this absolutely stunning, simple relationship between how long a planet's year is and how far it is from the Sun. The square of its orbital period is proportional to the cube of its distance. This simple rule governs literally everything orbiting our Sun. It's beautiful.
So how do we actually put this to work? Well, the easiest way is to set it up as a ratio comparing two planets. So we have the ratio of the periods squared on one side and the ratio of the distances cubed on the other. We know the period ratio is 12 to 1, so we square that and we get 144. That means the cube of the distance ratio has to equal 144. And right here is a classic trap. I see this all the time. Your brain sees a number like 144 and it just screams, hey, the square root is 12. But wait a second, you have to honor the law. The formula says the distance ratio is cubed, so to get it by itself, we have to take the cube root, not the square root. Don't fall for it.
And when you pop the cube root of 144 into a calculator, you get about 5.2. And there we have it, our first answer. Just from knowing its year is 12 times longer, we figured out that Jupiter orbits about 5.2 times farther from the Sun than we do. That is the incredible power of Kepler's law right there.
Awesome. Part 1, done. Now that we know where Jupiter is, we can figure out how fast it's moving. So for the next part, we're going to calculate Jupiter's orbital velocity and its acceleration. This means we're shifting from the rules of orbits to the actual forces that make them happen.
So here's the second part of the mission. And that phrase, heliocentric reference frame, don't let it intimidate you. It's just a fancy way of saying we're imagining ourselves sitting at the center of the Sun, watching everything from a fixed spot. It just keeps the math nice and clean.
Now this is where the physics gets really cool. I mean, why do planets even orbit in the first place? Think of the Sun's gravity like an invisible, unbreakable tether that's constantly pulling Jupiter inward. This constant pull is what provides the centripetal force, the force that keeps bending Jupiter's path into a circle instead of letting it fly off in a straight line. So the most important takeaway is this: the gravitational force is the centripetal force. They're not two different things, they're one and the same. Okay, to get the numbers we're looking for, we just need two basic formulas from our circular motion toolkit. First, velocity. That's pretty intuitive, right? It's just the distance of one full orbit, which is the circumference, 2 pi r, divided by the time it takes, the period t. And second, centripetal acceleration, that constant inward turning, is calculated as the velocity squared divided by the radius. Let's use our handy ratio trick again. It worked so well the first time. Since velocity is just distance divided by time, the ratio of Jupiter's velocity to Earth's is the distance ratio divided by the period ratio. And hey, we already know both of those numbers. It's just 5.2 divided by 12, which gives us about 0.43. Now, we happen to know Earth is zipping along at about 30 kilometers per second, so finding Jupiter's speed is now super easy.
Which comes out to about 13 kilometers per second. Now, just stop and think about that. Does it make sense? Yes, it makes perfect sense. To stay in a stable orbit way out there where the Sun's gravity is weaker, Jupiter has to move more slowly. If it was moving as fast as Earth, it would just fly right out of the solar system.
And we can do the exact same thing for acceleration. You know the drill by now. The formula is v squared over r. So the ratio of accelerations is the ratio of velocities squared divided by the ratio of the distances. We plug in the numbers we just found, and we see that Jupiter's acceleration is only about 3.5% of Earth's. And that works out to this incredibly tiny number, around 0.00022 meters per second squared. It's an almost imperceptible, gentle, continuous turn towards the Sun, and that's exactly what you'd expect for such a huge, majestic, slow-moving orbit.
So let's put all the pieces together. Let's step back and just admire the cosmic blueprint that we've managed to sketch out, all starting from that one single fact about Jupiter's year.
This table really lays it all out. Look at how beautifully it all connects. We started with the given, a 12-year period. Kepler's law then forced the distance to be 5.2 times greater. In turn, that larger distance and longer journey required Jupiter to move slower, at about 13 kilometers per second. And finally, that slower speed and much wider turn resulted in that tiny, tiny acceleration. See, it's all a chain reaction.
And that right there is the big takeaway. In orbital mechanics, these values aren't just random numbers you plug into formulas. They're part of a single, coherent system. A longer year demands a farther orbit. A farther orbit demands a slower speed. And that combination demands a gentler curve. It's all locked together by the fundamental laws of gravity and motion.
You know, this leaves us with a pretty cool thought. Kepler did this amazing work describing how the planets moved. Then, about a generation later, Newton came along and, with his law of gravity, explained why they move that way. It really makes you wonder, what are the big cosmic puzzles we have today? Things like dark matter and dark energy, where we can describe how they work, but we're all still waiting for that next Newton to come along and finally tell us the fundamental why.